I'd really like to welcome John Plain to give our seminar this month. So John has been a professor of atmospheric chemistry in the School of Chemistry since at Leeds since 2006. So he did his BA and his PhD degrees at the University of Cambridge and was a research fellow at St. John's College, Cambridge until 1985. He was then an assistant associate professor at the University of Miami, Florida, before moving to the University of East Anglia in the UK between 1991 and 2006. So John studies the aeronomy of planetary atmospheres and the chemistry of the interstellar medium. So specialization is in cosmic dust, its formation around evolved stars, and the effect of cosmic dust ablation in planetary atmospheres, the formation of meteoric metal layers, sporadic ion layers, air glow, noctilucent clouds, and coupling of chemistry with tides and gravity waves. Using a combination of experimental and theoretical studies of neutral and ion molecule reactions in the gas phase, satellite observations, and global modeling. John is the author of over 410 peer-reviewed papers, 17 book chapters, so H-index 76 and more than 23,000 citations. He's been awarded the Royal Society of Chemistry Prize in Reaction Kinetics and Mechanisms, the RSC Tilden Prize, the NSF Cedar Lecture Prize, EGU Wilhelm Birknes Medal for Atmospheric Sciences, and the AGU Marcel Nicolet Lecture. He was elected an AGU Fellow in 2017, a Fellow of the Royal Society 2020, and a member of Academia Europaea 2022. He's trained 29 PhD students and has 24 postdocs in his research group. So today, John is going to give a seminar titled Effects of Cosmic Dust in the Atmosphere of Earth and Venus. So thank you, John.
Thank you very much, Rosie. Right, and hello to everyone. Hopefully everybody who wants to has now made it to the seminar. And so let's get straight on with this, if it's working. Come on. Here we go. So what I'm going to talk about today is sources of cosmic dust in the Earth's upper atmosphere, then the process of meteoric ablation, which gives rise to metal layers of metal atoms. Then this leads on, in fact, led us into this much bigger problem, which is how to deal with small-scale gravity waves, which are responsible for a lot of vertical transport in the upper atmosphere. I'll then talk about effects, impacts, one of which is sporadic E layers, and work we're now doing with a chemistry climate model to study those. And then I'll end the terrestrial part of the talk by talking about meteoric ablation as an extraterrestrial source of phosphorus. We'll then switch to Venus and look at ephemeral ice clouds in the upper atmosphere of Venus, above 100 kilometers. And then I'll end up by talking about the mystery absorber in the Venusian clouds. And all of these topics are linked by cosmic dust in these atmospheres. So first of all, the sources. The main source of cosmic dust in both Earth and Venus is Jupiter family comets. So these are comets that have been captured from the Kuiper belt by the enormous gravity of Jupiter, and they're in very short period orbits of just a few years. A secondary source is the asteroid belt between Mars and Jupiter. Asteroids crash into each other and produce small particles which can then move into the inner solar system. And then there are longer period comets like Halley over here, which has got a period of about 76 years. Kuiper belt objects with longer orbits, and then comets from the Oort cloud, which sometimes only visit our solar system once. And if you just look at the zodiacal light, this is a picture taken from Chile. So the sun is just below the horizon and illuminating this cloud of dust in the inner solar system. If you There's another photo here. If you just take a cut through that and plot the intensity, which is the black line here, above and below the plane of the ecliptic of the solar system, and then you plot what models predict the dust would, how it would be distributed above and below the plane of the ecliptic if it came from Jupiter family comets in red, the asteroid belt in green, which is a very nearby source, and so it's very narrow around the plane of the ecliptic, or these longer period comets, which are much more broadly spread. If you just looked at that picture, you'd straight away say most of the dust is coming from Jupiter family comets, and all the evidence points to that being correct. When the dust enters a planetary atmosphere at speeds, in the case of the Earth, hypothermal speeds between 11 and 72 kilometers a second, collisions with air molecules rapidly heats it up. And if it melts around 1800 Kelvin, the volatile elements sodium, potassium are released. It then gets to 2000 K, the main elements, which are iron, magnesium, and silicon, because the constituents of the common forms of cosmic dust are essentially olivine, and smaller amounts of nickel here, which I'll be coming back to a bit later. If it carries on heating further at about 2400 Kelvin, these elements here, the so-called CAT elements, calcium, aluminium, and titanium, will ablate. So they're the most refractory. And this whole process here is captured in a model that we have developed called the chemical ablation model, CABMOD, which enables you for a particle of a given size and entry velocity and angle to predict the heights at which these different elements will ablate. If the particle does not completely evaporate, this little molten bead will condense to form a glass-like particle called a cosmic spherule, which will then fall to the ground. And before the particle melts, organics are lost. These are the glue that holds together the minerals inside the grain. And this can lead to fragmentation if the glue fails early on. So the injection of metals into atmospheres creates layers of metal atoms. This is for the Earth now, and I've shown on here 5 different elements. And these can all be observed from the ground using the laser radar or Lidar technique. And I'll show you some measurements of nickel in a moment. If you take these 5 elements and integrate across the layers here, you get what's called the column abundance. And if you plot or correlate the column abundances of those elements, and I've also put lithium on here, which was measured quite a long time ago, against their relative abundance in chondritic meteorites, then you see the 3 alkali elements lie fairly well on a one-to-one correlation. But these elements here show increasingly fall below the line. In other words, they don't ablate as efficiently. Calcium in particular is depleted by over 2 orders of magnitude. And this just simply reflects differential ablation. And the CABMOD model that I referred to on the previous slide predicts, for example, these are the injection profiles of iron, sodium, and calcium. They have quite complex shapes because we're integrating over the populations of dust from the different sources that I referred to. And well, you can see iron has the biggest injection, then there's sodium because there's about 15 times more iron than sodium, but calcium, which has a very similar abundance to sodium in chondritic material, is very, very depleted, and that's why it's fallen so far below the 1-to-1 line. So meteoric ablation injects metal atoms, and the interesting question is why they then occur as a layer of atoms, because metals love to be oxidized, things like sodium and potassium extremely reactive. The reason is the following. Below 85 kilometers in our atmosphere, the atmosphere is strongly oxidizing. There's lots of ozone, molecular oxygen, and so on, and the atoms are removed as compounds. These in turn cluster together, things like hydroxides, oxides, carbonates, to make small nanometer-sized particles called meteoric smoke particles. And then in the ionosphere, there are ambient NO+ and O2+ ions which charge transfer with metals very, very readily to make metallic ions. And it's just this region here where there are very high concentrations of H and O atoms that you get what a reducing atmosphere. So this is more like what the atmosphere was like before the great oxygenation event. And these compounds, whether they're ions or neutrals, are reduced back to metal atoms by O and H. I was recently involved in an attempt to find if there was a nickel layer on in the Earth's atmosphere, which one would certainly predict. So this is a Lidar cartoon. You fire up a Lidar in the near ultraviolet just at wavelengths long enough so that it penetrate the stratospheric ozone layer, which would absorb at shorter wavelengths, and you wouldn't be able to do this. So this is a pulse laser. The nickel atoms here fluoresce if you've tuned the laser correctly, and you can pick up some of the photons at the ground with the telescope and do time-resolved photon counting to get the range. So what you find is that there's Rayleigh scattering of the light as the pulse travels up through the atmosphere. This is on a log scale, so it's nearly linear, and it almost disappears here into the noise, and then you get a clear evidence of a layer, and that's fluorescent, resonance fluorescence. And there's a sort of complicated spectroscopy of nickel that you can employ to your advantage. It's a transition metal, so it's much more complex than something like sodium. It's very simple. And here is an actual result when the noise is subtracted. This shows the signal. So there is a layer above 85 kilometers, and here are the actual layers. So this was the first definite identification of the nickel layer. These measurements were made at Kühlungsborn on the Baltic coast in Germany. So we then went into the lab and measured a lot of reactions, and these are all shown in this schematic. Now, all of the schematics I'm going to show today, it's not a detailed chemistry lecture. They all have the same format. So iron species, charged species, are in blue boxes, neutrals are in green boxes, and then these arrows show reactions that connect them, and a lot of these have now been measured in the case of nickel by my group, and you can then construct a model where you have some sort of chemistry where nickel is ionized by charge transfer principally, and then you have various reactions here to make molecular ions which undergo dissociative recombination with electrons back to nickel. On the neutral side, so this is on the underside of the layer, below 85 kilometers, you get oxidation, making nickel oxide, and then various other oxides, and then the rate of water and CO2 is to push around here until you get to nickel hydroxide, which is the sort of immediate sink for the metal. And we use things like laser flash photolysis and fast flow tubes to study these reactions in the lab. And obviously I can go into that in much more detail if anybody is interested, and there are some relevant papers. So you can take that chemistry, that chemical network, and put it into a model. The one that our workhorse is the whole atmosphere community climate model, WACCM. So we put that into WACCM, and then we can model the nickel layer. Here it is peaking around 85 kilometers as a function of month of the year. That's altitude, obviously, and this is the concentration or density. And here are some measurements made by our collaborators at the Space Weather Institute in Beijing. And the agreement is very good. And what you see here is a midwinter maximum and then a midsummer minimum. When it gets much colder, the chemistry slows down. That returns the nickel from its various compounds back to atoms. You know, and so that is, just bear in mind that there is good agreement here, but as we'll see in a moment, this requires something to be done to the nickel injection rate that I have used in the model here. Just to show you that there is some experimental evidence for these chemical networks actually working. This is a rocket experiment that I took part in a few years ago from Andøya in the north of Norway. And the idea was for the rocket to go up to, it went about 130 kilometers, but to pass through where the sodium layer was, and then to have a Lidar that looked at the sodium layer very near where the rocket went. And in fact, luckily, they actually passed very close to each other. And this is the result. Here is the sodium layer in black, measured by a Lidar on the mountain at the Alomar Observatory beside the rocket range. And this is the atomic oxygen profile that was measured on the rocket payload. And you see a very, very nice correspondence here showing that atomic oxygen plays this enormously important role in keeping the sodium in the form of atoms and not allowing it to become oxidized into molecules. So having worked on this chemistry for a while, one then wants to know what is the actual amount of cosmic dust coming into the atmosphere. And when we started this about 12 years ago, the estimates ranged by actually 2 orders of magnitude, from 3 to 300 tons a day. So the way we've done it is the following. You can take a Lidar and measure the vertical velocity of sodium or iron coming down in the atmosphere, and also the concentration. And if you take a product of the concentration and vertical velocity and average it, that gives you a flux. And you can measure the flux. This is at the Starfire optical range near Albuquerque. And the flux of both these metals is negative, as it should be, because conventionally that's downwards, and it's essentially zero up here, but below the altitude at which all of the metals should be in the atomic form, it becomes significantly negative, and then it starts to disappear again because the metals are being oxidized. You can use those measurements to get a flux of sodium and a flux of iron. You can also go to the South Pole, and underneath the base here, there is a large water tank, a water well, where the ice and snow have been melted. You can see on the scale here, this is a very, very big volume has been melted. These are cosmic spherules. So remember, they're the little cosmic dust particles that re-solidified They didn't completely evaporate, and they're easy to spot. You can basically suck them out of the bottom of the well here and identify them just from this very obvious appearance. You don't confuse them with flakes of rust or something. And this gives you a flux of cosmic spherules. So you now have the fluxes of three things. We then go to a model of cosmic dust in the solar system for the three sources. Remember, Jupiter family, asteroidal, and long period comets. We can put those through the chemical ablation model. And this gives us a rate of injection of sodium and of iron and of cosmic spherules for each of those sources. So now we have three simultaneous equations. The flux of sodium, or the flux of iron, or the flux of spherules is equal to the flux of each of these three different dust sources with some weighting coefficients. And you can solve the three equations to get the three unknowns, alpha, beta, and gamma. And it's an unambiguous solution. Here is the result. The total amount of dust coming into the atmosphere is around 28 tons per day, almost the geometric mean of that range between 3 and 300, as it turns out. Most of it, as you can see here, is coming from Jupiter family comets, around 70%, very little from the asteroidal belt, and a modest amount from long period comets, but they contribute most of the ablated atoms here, 5 out of 8, because these particles which have come from these long period comets enter at very high speeds, so they all essentially evaporate. Right. So you might say now that all looks great and there's been other measurements since. Don't have time to go into. Have we now solved the cosmic dust input? And there are two issues that still needs to be sorted out. And the first is that the rate of deposition at the surface don't appear to be large enough. So this is a paper that I was involved in, which was published in the Christmas issue of Nature back in 2004. This lovely picture of a big fireball of snow and an aurora. And sorry. And what we did in that was to measure the accumulation of two cosmic elements, iridium and platinum. So these elements are very depleted in terrestrial dust, and so if you find significant concentrations of them, you can differentiate between the cosmic input and the terrestrial input. And so the measurements were made up here in the middle of Greenland and also at two sites in Antarctica. And basically we then took this global model WACCM and worked out for these inputs of sodium and iron that we have now settled on in the upper atmosphere, how much of this meteoric smoke should form and where it would be deposited. And essentially it mostly comes in, as you see, at mid-latitudes in both hemispheres, because it works its way down the winter polar vortices, which sort of hoover up all the air from the upper atmosphere. The dust is exported in the lower stratosphere and enters the troposphere, where you get a lot of tropopause folding caused by storm tracks up here in the North Pacific and the Atlantic and down here in the Southern Ocean. Not too much is being deposited where the pink points are, and in fact, the measured deposition rate is 33 times higher in Greenland, and a big factor, a significant factor also in Antarctica. So this is an unsolved problem, which there are various possible explanations for. Very hard to make these measurements. You have to use ultra clean conditions because the concentrations are absolutely tiny. We talk about 10 to the minus 15 molar. in these ice samples. So that's one possibility, or something else which might be more interesting. Then there's a second problem, and that is modeling the meteoric layers themselves. I showed you how we got great agreement for the nickel layer, but what I didn't mention is that we had to then reduce the input of nickel from this CAB-MOD ZODI model that I just showed you. We have to reduce that by a factor of 5, which is quite a big factor. Let me show you this in the case of sodium. This is the sodium column abundance that you predict from WACCM using that measured sodium flux in the mesosphere. And this is latitude here and month of the year. You see very little equatorial variation, but you see a big increase in midwinter and then a deep minimum in summer, and the reverse here, not quite as marked. Let's now compare with measurements on the same scale, and you see things don't look so good. Obviously, the seasonal variation is being captured reasonably well, but the absolute amount of sodium is about 5 times smaller. Chester Gardner, who's at the University of Illinois, has identified a problem in the upper atmosphere, and that is, or modeling in the upper atmosphere, and that is that small-scale gravity waves, which don't actually break and contribute to turbulence, but are simply dissipating, create a large vertical flux. And these small waves, so we're talking about wavelengths much less than 100 kilometers, are not resolved in a global model, which necessarily has to have a grid box of a degree by a degree or whatever. And so these unresolved and unbroken waves are not resolved, and they should contribute to vertical transport. And he has developed a parameterization for that. We put into WACCM, and this is the result, which is obviously in much better agreement with the observations than without it. But that's a parameterization, a lot of sort of heavy-duty maths. The question is, does that really happen? And so to do that, we have looked at vertical transport using WACCM, but now with a regionally refined version. So let me show you what that means. This is the normal grid spacing of WACCM 1 by 1 degrees. And what is done in this case is we focus on the continental US and use a mesh that is much finer, an eighth by an eighth of a degree in here, and then there's a sort of transition region back to the global grid outside. And so that means that we can, and we turn off any parameterization of gravity waves inside this region in order to look at the difference when you have small scale, the small scale here, the RR version, as I will now call it, versus the standard version where you do not have regional refinement. You just have the normal grid size 1 degree, which is about 111 kilometers. 14 kilometers is the 8th degree. The reason you have to do this, of course, is simply that to run a global model at this sort of resolution, it would just be impossibly expensive. Okay, so here we have temperature, and what you're seeing here is the temperature at 4 different heights in the atmosphere. The top row here is the normal version of WACCM, and this is the regionally refined version. So they're both showing this conus area over the continental US. And you can see straight away lots of gravity waves being resolved in here, which are not resolved in the standard version of the model. And some of this, particularly these sort of obvious concentric rings, seem to be driven by hotspots in the lower atmosphere. And if you now look at a similar plot, this is a vertical velocity in meters per second. This is what we're particularly interested in. You see much more structure is being captured, of course, at higher resolution. And some of these velocities instantaneously are actually pretty large, going up as far as 4 meters a second vertically. Obviously, that can't go on for very long. And this makes a very important difference. And what is generating this is basically strong upward convection from the troposphere, created in this case by thunderstorm type convective events. This is nitric oxide. Now, same altitudes, cuts through the atmosphere. So I'm not going to play that. It's not good to try this. Nice. Just try once more. Okay, this one doesn't want to play. So nitric oxide has significant sources in the ionosphere produced by energetic particle precipitation. And we can see that although these are sort of similar up here in the lower thermosphere, at 85 kilometers, there's clearly a lot more NO being brought down. You also see lightning knocks being produced in the troposphere. That seemed to be the source of these waves. This is a vertical plot here of the NO flux, and the orange here is with regional refinement and the blue is without. And you see this negative flux, because it's downwards from the lower thermosphere, is significantly enhanced when you capture the smaller scale waves. And this just shows the ratio. So you see the NO down here in the middle mesosphere is something like double compared to, and it's then reduced in the lower thermosphere by this effect. CO2 is coming up from below, so there's an upward flux of CO2, and again, as you would expect, these small-scale waves are increasing vertical transport. Now it's upwards, so it's positive here. So that, remember, that's RR and that's non-RR. And so what we see here is a big increase in CO2 in the lower thermosphere as a result. More interesting is atomic oxygen, because this controls almost everything chemical in this region, and most atomic oxygen is made by photolysis of O2 above 95 kilometers and then is transported downwards. So it has a negative flux, significantly bigger in the case of RR. And this leads, as you see here, to roughly double the amount of atomic oxygen down here in the region where the metal layers occur, for example. And the result with ozone is that ozone increases. So there's this maximum of ozone up here in the mesosphere. When you add in short wavelength vertical transport, you see almost doubling. That's the ratio plot there. And this has been a long-standing problem, is that models were not able to account for the observed ozone in the upper mesosphere, but it does seem to be due to gravity wave, short wavelength gravity waves being unresolved. Right, now let's talk about some impacts. So the first one I want to talk about is sporadic E layers. Most people, I'm sure, know about these, but the classical formation mechanisms where you have an eastward wind at one altitude in the ionosphere and a westward wind above it. So you have a wind shear, and these are the field lines heading northwards. This produces a convergence at the shear here of the ions and enhanced electron density. And these very high concentrations of electrons that are possible because metallic ions are very long-lived. They are only destroyed by radiative or dielectronic recombination with electrons if they can't form molecular ions, and they can't really do that above 105 kilometers. So what we've done is take the extended version of WACCM-X that goes up to the top of the thermosphere, and we put into it a self-consistent transport of metallic ions, so full electrodynamics transport of these ions in the magnetic field, and we can then run it. And what we don't do is look for layers of electrons, because there are always lots of electrons around just in the background. What we do is look for concentrated layers of metallic ions. And so here you can see a layer of Fe plus that is descending with the tide. So it starts off in the early afternoon and it comes down here, and is then dissipated by chemistry in this case, because it's reached this altitude where ozone starts reacting with Fe plus. And what we were interested to do was see how well we could predict the occurrence frequency of sporadic E using WACCM-X with the metals in it, and compare that to measurements made with the cosmic satellites. Or satellites, there are still more than one, I think, operating. So the red here shows cosmic, and this is the shaded area gives you an idea of the variability of the measurement, spring, summer, autumn, winter in the Northern Hemisphere. And blue is the WACCM-X prediction. And notice the cosmic abundance has been divided by a factor of 2. We think that is probably okay to do here, because the way that you determine if a sporadic E is present is a little bit different between them. But the most important thing is to see whether the model is capturing the seasonality correctly. So it does capture the fact that there are more in the southern, summer, in the northern hemisphere, here in the southern hemisphere than in the winter, and you get this more or less even spread during the equinoctial period. So that's looking sort of promising. If you compare the local time dependence of sporadic E, this is WACCM here, and here is cosmic. You can see this really looks quite good. So this is local time versus latitude. There always tend to be these 2 blobs of higher frequency occurrence either side of the geomagnetic equator, and that is sort of quite well captured. So this is looking good for the future. All right, let's move on to phosphorus for those people who are interested in the origins of life and so on. Phosphorus is a key biological element, and its dominant form is phosphate, where the phosphorus is in the +5 oxidation state. Now the problem with phosphate is it's quite insoluble in water. It's very difficult, therefore, to use it biologically. Much better, and so it's a limiting factor for life. Much better is to use reduced phosphorus, like phosphonates, anything with an oxidation state of 3 or less, because these are much more soluble and reactive, and so they can be exploited by biological systems. And so there's been a lot of speculation about the role of phosphorus in the origins of life. And for example, in the late heavy bombardment period, which was a few billion years ago, early on in the Earth's history, a lot of meteoritic material fell to the Earth, and there's been a focus on whether the phosphorus in contained as metal phosphide, so this is where the phosphorus is in the -1 oxidation state, could have been leached out by aqueous chemistry to produce biologically available phosphorus. However, we entered into this because you have to recognize that most of the mass of extraterrestrial phosphorus entering any atmosphere is going to be in interplanetary dust particles in the 1 to 100 micron size range, not big meteorites that survive entry, fall to the ground, and then undergo leaching. And there are some of these interplanetary dust particles that have been captured in the stratosphere. The phosphorus is about 0.1% by weight, so it's not insignificant. And if most of these dust particles ablate, that should inject the phosphorus into the upper atmosphere. And then the question is, does the subsequent chemistry produce phosphate or a reduced form of phosphorus, which could then descend to the surface? So the first question for us is, what is the dominant form of phosphorus in these in cosmic dust particles? And to do that, we went to the diamond light source in a collaboration with George Flynn from Stony Brook, who has a sample of from the NASA collection, which we were able to use to analyze the phosphorus and see what form it was in using X-ray fluorescence spectroscopy. And we showed it's almost all in the form of phosphate, which is actually not biologically available. However, when we studied this in our meteoric ablation simulator in Leeds, so this is where we put these are meteoritic fragments on a filament here, heated it up, we can go up to 3000 Kelvin in about 3 seconds if necessary, just tracked with a pyrometer. We can then use 2 lasers that come through this reactor system just above the filament, as shown here. There's the filament, and measure what's evaporating by resonance fluorescence. And we could tune the 2 lasers, in this case, one of them to look at PO, which is actually how the phosphorus evaporates in the form of PO rather than atomic P, and also calcium in this case. And we were able to show that the phosphorus essentially is ablating as phosphorus oxide. Now, again, I don't want to go through the physical chemistry too much here, but you can then look at reactions like any atomic P that's formed, will undergo reactions very fast with O2, and then how that goes on. These are so-called potential energy surfaces. So these are, those who don't know, calculated using ab initio quantum theory or electronic structure theory. And when you have a surface like this, you can calculate rate coefficients. That's what you need in an atmospheric model to work out how fast these reactions will occur. And so these are just some examples here showing how you might start to get to, for example, the phosphate or the phosphites. So this is H3PO3 is the +3, that's the biologically active one, and that's the one that is not very biologically active. And so you now can create one of these schematics. Remember, green boxes are neutral, blue are the ions. And what we have here is the red route that we identified, which is how you form phosphate, or the green route for good, which is how you can make phosphite. And so all of this now comprises the WACCM-P model. And this is where we predict what is going to form, and the only thing to note here is that the two main forms of phosphorus below, where there should be a nice layer of OPO, which might be optically detectable one day with better instrumentation. Below that, there's phosphate and phosphite. And this is where we predict the amount, how these change as a function of season and so on. That's not terribly important. Let's look at where it's deposited. As you would expect, what I was saying earlier about storm tracks and so on, the deposition is mainly at these mid-latitudes. Here, you can see wherever you've got mountains like the Rockies, the Andes, or the Himalayas, you get a lot of deposition of the phosphorus compounds there. Very, very little at low latitudes, because it's all come down the polar vortices and they've been exported through tropicals folding at mid-latitudes. And globally, about 11% of the ablated phosphorus should be in this active form. And so this might have been a very important component of life developing, as I say, 3 billion years ago, or whatever. Right, now noctilucent clouds, I guess most people know in the audience will know what those are, and I don't want to say any more about them here, except that the water ice of which they're composed is almost certainly condenses onto meteoric smoke particles. So let's now ask the question, could you get ephemeral ice clouds in the upper atmosphere of Venus? Everyone knows Venus is hellish at the surface. Temperatures of 700 Kelvin, very volcanic. We'll see that why that's important later on. And then if this is a radar image, if you look in the UV, you find it's completely covered by clouds, but with these interesting dark patches here where there's strong absorption, and that we'll also come back to in a moment. I don't know why that's not playing. Let's not just see why. It's obviously just some glitch. That's better. Okay, here it is. So here's the temperature profile, the black line. This is the average temperature profile, hellishly hot down here, but you can see that once you get above 80 kilometers, it's around 200 Kelvin. Here is where these ice clouds are, sorry, not the ice clouds, the sulfuric acid droplet clouds, hazes, and so on, which completely enshroud Venus, extend over this height range. Meteoric input is up here, peaking around 115 kilometers. And what we noticed is if you look at the actual measured temperature profiles up here, for example, from the SWAR instrument on Venus Express, there are occasions where the temperature falls for a short time to very low, below 100 Kelvin. And that is actually low enough either to make water ice or even CO2 ice clouds. And so we wondered under what conditions one might see that. So what we did was actually modeled for given SWAR temperature profiles what the where these ice clouds would form. And if we just take this really big one here, so this is actually the size against height. These are particles bigger than 1 micron in radius, so big clunker. And this actually started up here. So this is where the very cold region was. And of course, this grew very fast because down here, there's plenty of CO2, relatively speaking, to condense. It's the main constituent of the atmosphere, and it's basically plating out on little metal carbonate particles. And Of course, it grows very quickly, which means it falls very quickly through the atmosphere until it enters a warmer region of the atmosphere, and very quickly the CO2 sublimates and it disappears. So the blue are actual clouds we predict would have occurred at very high latitudes, and red is at somewhat lower latitudes. The really big ones seem to be restricted to the very high latitudes. But these are a little bit like Virgo clouds in the terrestrial atmosphere, and here are two pictures of them. So this is where you have a cloud and you can get precipitation, water, or droplets or ice, which fall from this cold region down through the atmosphere until they enter a warm region and evaporate. They don't reach the ground. There's another nice picture over there. And this just shows a model sensitivity study for one particular example, where one of the unknowns here is the uptake coefficient of CO2 onto the growing particle, which that will be a number between 1, the maximum, and 0, which would be the minimum. The most likely is probably up here between 0.05 and 0.1. The smaller it is, of course, the smaller the cloud, but the basic shape is always going to be the same because this is the warm region where sublimation occurs. So that's the model. Now the question is, could you observe these? And this here is the detection limit of the SWAR instrument, operating at 220 nanometers, a near ultraviolet, where you get very strong extinction from particles. And this here shows the predicted extinction from the different predicted clouds, and all of them, apart from where you have an unfeasibly small uptake coefficient, should be detectable. But there's a big challenge, and that is they only last for a few minutes because they form up here and they drop really rapidly because the pressure here is so low, and then they're gone. So you have to be in the right place at the right time, where you get this deep cooling produced by some sort of rarefaction of a big wave. The cloud forms, and before it has a chance to sublimate, you can see it. So that's something maybe for the future. Right. Last up then is the absorption in the Venusian clouds. So this is a visible light picture, and you see Venus looks extremely boring. If you look in the UV, this is at 365 nanometers, there's clearly lots of structures going on, and it's this strong absorption here that we are interested in. This has been a very long-standing problem, going right back, in fact, to the 1920s when this was first observed. And the best spectrum we have of the what's called the mystery absorber is from the Messenger spacecraft when it did a Venus flyby on the way to Mercury. And here is the measured spectrum. It's this dashed line here with an envelope of uncertainty. You see it extends right out into the green, almost to the orange part of the visible, and then it's very strong here in the ultraviolet. And here are some candidates that have been proposed. Iron trichloride, S2O is another, but that obviously doesn't fit very well. The one that fits best on here is a dimer of sulfur oxide, SO or OSSO. And what we decided to do was investigate whether OSSO was a possible candidate, and then also to look at iron trichloride. So to do that, we use the Venus planetary climate model from the LMD Latmos group in Paris. So this has got 3D dynamics, a whole atmosphere model, and it's got photochemistry. And then to look at the expected absorption spectrum, we used a radiative transfer model developed by the Met Office called Socrates. And so this allows for multiple scattering. It's a 1D radiative transfer code. So let's start with OSSO, and there are two forms of it, the cis and the trans. You can calculate the rate at which those form from SO, which is observed. And this is then lost due to photolysis, which is why it's got that UV near visible absorption. It thermally decomposes because there's not a very strong bond between the two sulfur atoms. And we also calculated the rates of reactions with things that are prevalent at this altitude, O, chlorine, and CO produced from photolysis of CO2. And this is the predicted amount of OSSO in the two forms at, and you see there is this broad layer. This is a log scale note, but there's this broad layer up here peaking around 60 kilometers. So the question is that enough? And what this is showing here is the total atmospheric reflectance against wavelength. This is the messenger spectrum over here, showing this absorption starting around 500 nanometers and then going into the UV. And if you just had pure sulfuric acid clouds, this is what you would observe, this light blue line. And it's this difference here that is the source of all of this mystery. If you put in the dimer, unfortunately, this makes almost no difference up here. And if you increase the amount of dimer, you get a blue line here. If you change the predicted fraction of cis to trans, you can get a slightly better fit, but you're not really capturing this out here. And in any case, there's no reason for these rather large increases in the dimer because they're really not that stable. And the fact they absorb light means they're photolysed very quickly. So that doesn't seem to be a starter. So the grad student, Jo Egan, who is working on this, almost completed her thesis now, went back to look at iron trichloride. That's the spectrum of iron trichloride I showed you in the earlier figure. It's clearly absorbing nowhere near the messenger spectrum in black. But this spectrum was taken a long time ago in ethyl acetate, and iron trichloride will certainly not be dissolved in ethyl acetate in Venus atmosphere. So what Jo did was to dissolve anhydrous iron trichloride in 80% weight sulfuric acid. And you can see the spectrum she has produced is much closer to the observation. And another thing that she does in these experiments is she adds a lot of HCl. It's very important to do that. Otherwise, the iron trichloride reacts with the sulfuric acid and you get iron sulfate. But if you have a lot of HCl present, and you do in Venus atmosphere, that keeps the iron trichloride intact. So here we have the same plot I showed you earlier, top of the atmosphere reflectance, the gray crosses are messenger. That's just the sulfuric acid. And now when you put in around 1%, well, this is 0.6%, that's 0.9% of iron trichloride, you can see you get a very nice match. And so we are now pretty convinced, took a lot of time to convince me, but Jo has pushed this from the start, that this absorber is iron trichloride. So how is that being produced? Well, we have an injection of iron from cosmic dust ablation that reacts with ozone and the resulting FeO recombines with CO2 and you get iron trichloride. Hydrogen chloride is being released from volcanic activity at the surface, and there's a very significant concentration in the upper atmosphere of Venus, which is measured. Those two undergo a series of reactions. This is essentially a base or an alkali, and that is an acid, and you end up with iron trichloride. So when you now work out how much there might be, this is altitude here against concentration. There's the HCl just to show you how much there is available for this chemistry. And then once the iron trichloride is formed and it is in the droplets of the clouds, to stop it reacting away. This is the amount of iron that is produced by meteoric ablation, peaking up here around 110 kilometers. And the model predicts that most of the iron is either iron trichloride or even more iron trichloride bound with CO2, which doesn't change its spectral features. So here is a movie showing what happens over a couple of Venus days, which, remember, Venus day is over 200 Earth days. So it takes a long time to run this model. And what you are seeing here essentially is the iron trichloride starts up here. It tends to follow this circulation pattern here and fills in at lower latitudes as time goes by. Because the model takes so long to run, we then went to a 1D model to look at this in more detail, and this shows that up to 40% of the observed absorption from the messenger spectrum, for instance, can be explained by meteoric iron. Now that 40% has a big uncertainty on it, and I think that we're at the point now where we would say that is the main absorbing species, and that is the mystery absorber. So let me end by acknowledging my various collaborators. These are people at Leeds. Tasha Aylett did the Sporadic E work, Joe Egan the Venus work, then Marcin and Vittoria Guarino, the gravity wave work with the RR model. Dan Marsh and Wu Hufeng are probably well known to people in the community. They are the WACCM modeling team. And then internationally, there's a whole bunch of collaborators here contributing in various ways. So I will stop there and take some questions if there are any.